say that what we have done so far, that we try to motivate the tight binding model by simply doing this what I call linear combination of atomic orbitals, bringing two hydrogen-like atoms together, and we showed that you get simple ideas of bonding, anti-bonding states, and then we saw glimpses of that also in terms of a double well potential, the double oscillator. From that we built up the tight binding model. So that we did last week. And today we set up the graphene problem, as we said, that graphene is basically a two-dimensional sheet of carbon atoms on a hexagonal honeycomb lattice. This lattice comprises two interpenetrating triangular lattices. So we have a sublattice and a B sublattice. And then what we did is that we set up the simplest tight binding Hamiltonian on that lattice, assuming that the sigma bond that you create by having sp2 hybridized carbon atoms will then have this possibility that you can have an excitation like an electron hop from an A sublattice to a B sublattice. We carefully delineated all the important lattice vectors, the nearest neighbor vectors, the primitive vectors, and what happens in the reciprocal space in the first Brillouin zone. Then looked at these k prime points in the Brillouin zone. And then from that simple tight binding Hamiltonian with a constant hopping energy, which we call T, the hopping integral, we went to the Fourier space and showed that you have, when you diagonalize the system, you have a Hamiltonian whose energy eigenvalues have split, and astonishingly what is found out, that near either the k or the k prime points in the Brillouin zone, when you expand things, the energy around that k or k prime point, you find out that the energy goes linear in the wave vector. So this linearity is very different from the usual dispersion relations that we encounter in solid-state physics, which most often is quadratic. So this linearity, therefore, is very similar to what happens in the physics of completely different areas of relativistic electrons governed by the Dirac equation, where the energy has a rest mass term, energy squared is m squared c4 plus p squared c squared, and the extreme relativistic case is the one in which you can drop the rest mass energy, and so in the extreme relativistic case, energy is Pc. You know what is an extreme relativistic case. For instance, take a photon. Now the photon, photon has an energy h nu, okay, and its momentum is h nu divided by c. So that's an example of an extremely relativistic case. Now in graphene we find out that in some sense we are actually in the extreme relativistic case because the energy does not depend on the mass of the electron at all or on the effective mass. Furthermore, the linearity in energy with respect to k vector or q vector has a coefficient which has the dimension of an h bar times the velocity, and that's the Fermi velocity. You can estimate the Fermi velocity because you know, so that Fermi velocity depends on the basic lattice spacing, which we said is about 1.14 nanometer, and you also put in the hopping energy, and you find that its Fermi velocity is of the order of 10 to the 6 centimeter a second. So it's therefore much smaller than the speed of light. So we are talking about a solid-state problem, although the energy momentum gives you something like a relativistic, massless Dirac fermion kind of picture. So having said that, remember last week we were also saying one very important tool to probe such two-dimensional system is a magnetic field, because of course you have heard that Nobel Prizes have been given on the last year, the new physics in the two-dimensional systems. Of course, the work was done much earlier, like Howells and others. But also quantum Hall effect probably has got how many Nobel Prizes? Doctors?
I think there are two at least.
At least two, right? Yeah. For Klitzing, and then for the fractional one. So, so it's a very exciting area, and in order to see quantum Hall effect, of course, you have to see how the system will respond to an applied magnetic field. So last week, what we did is to actually look at how the hopping integral acquires an additional phase factor, additional magnetic field dependence due to the vector potential and due to what is called the Aharonov-Bohm effect, and we saw that how hopping gets altered, and if hopping gets altered, then properties like diamagnetism, properties like bond current will change, and we showed that even if you're dealing with normal state electrons, you will get a bond current. It's sometimes called persistent current and mesoscopic ring. So we did an example of a 3-side mesoscopic ring. But so the whole point is that it's very important to study the effect of a magnetic field on such systems. And so what I will do today is to again remind the students, very elementary stuff, remind the students what happens to a charged particle in a magnetic field. Okay? And then we build it up from there and do things like Landau diamagnetism. So this is really undergraduate stuff that we do. So first is quantized cyclotron motion. So you know the equation of motion of a charged particle in a magnetic field is m dv dt is minus E v cross v divided by c, right? Nothing else. I assume that there is a magnetic field along the z direction, and here is your Newton's equation of motion. This is what is called a Lorentz force, right? So now, because the magnetic
joke, I'm sorry.
x component of this, what will be the x component of this vector? So how do you calculate v cross b? V cross b, you can do it in the old-fashioned way. It's not the correct way sometimes because you have a non-commuting operator, you have to be careful. But let me do it in the old-fashioned way. Otherwise, you have to use the tensor notation. But so you write a determinant like this. So you have Vx, Vy, Vz. This is the old-fashioned way, and the B only has a Z component. Therefore, that is why you have zeros here. So you can easily see that if you complete the determinant, then this is I hat Vyb plus j hat, this times 0 minus this, so minus j hat Vxb. Right? That's the answer. So I'm looking at the x component. So for the x component, the relevant term is only this. So I have E by C, Vyb, and M. So now I can take M here, okay, and this EB by MC is, so I'm assuming that this is, I've already taken the sign into account of an electron, so this is actually the magnitude of the charge. What is EB by MC dimensionally? Okay, you can check that this is the dimension of a frequency, and in fact it's called a cyclotron frequency. It will be clear why it is called cyclotron. So this is minus omega c Vy, and I write down dVy dt. You'll pick up a positive sign because of this. You'll pick up a positive sign because two negative and this negative will combine, and you'll get omega c Vx. So this is right? So this is one of the simplest sets of coupled differential equations where equation for Vx is coupled with Vy and equation for Vy is coupled with Vx. A very easy way of solving this is actually to go to a plane polar coordinate and introduce what are called, V plus and V minus. So you define V plus as Vx plus I Vy and V minus as Vx minus I Vy. So V plus and V minus are just complex conjugates of each other. So what you do is, suppose you multiply this term by imaginary I and you add, then on the left hand side you get ddt of V plus, right? Because you'll get Vx plus I Vy, and here you'll get an I here, so you get an I omega c Vx, and there's a minus sign here, so it will get again, so now the equation gets decoupled. And similarly, dt Vy dt V minus, what you do is you multiply by x and I and subtract. So on the left hand side you get ddt V minus. When you subtract, you get minus I omega c V minus x. Yeah. Let me just check if I put my signs right. I goofed on the sign. So this actually is minus and that's plus. So what you have achieved by doing this trick, this is something like going from xy to Argand diagram. So we go into the complex conjugate, x plus plus iy kind of thing. So now you have decoupled the two equations. So now V plus depends only on V plus, V minus depends only on V minus, and the solutions are very easy to write down. V plus minus of t is equal to, in fact, e to the power minus plus I omega ct V plus minus 0. So you can easily see that why V minus and V plus are just complex conjugates of each other when you flip the exponential. And if you now from V plus and V minus go back and obtain what are Vx, because Vx after all is half V plus plus V minus, and Vy after all is 1 over 2i V plus minus V minus. So now I can construct, and you can easily see that you have circular motion in two dimensions. Vx of t is Vx of naught cosine omega ct plus Vy of naught sine omega ct, and Vy of t is just phase shifted, is Vy of naught cosine omega ct minus Vx of naught sine omega ct. So physics is very clear. You have a charged particle moving in a magnetic field, and then the electrons in the plane normal to the magnetic field have circular motion, because this is the solution of circular motion. Okay, one going in the clockwise direction, the other going in the anti-clockwise direction. Okay, and this is exactly what you do to get circular polarization also in electromagnetic fields. And so these things go in circle. The electrons go in circle. That's why it's called cyclotron motion. And why it is of importance, because the charged particle moving in a circle is an accelerated motion because of the Lorentz force. An accelerated charged particle will radiate. This radiation you capture and you get synchrotron, etc., etc. So this is why it's called cyclotron motion. Still, everything is classical, and of course you can quantize a system and look at quantum mechanics. So what happens when you do quantum mechanics? But before that, there is just old-fashioned way of doing things to get some idea of characteristic length scales of the problem. See, basically what is happening is anything that goes in a circular motion, if you recall that the particle moving in a circle experiences what is called a centripetal force, right? A This is why when you go in a car or a bus and turning around, you have to lean against something because you have to balance that centripetal force. Balancing force is called centrifugal. So basically what is happening is that the centripetal force, suppose this radius is xi, then you know that the centripetal force is mv squared by xi, and that is balanced by this Lorentz force. So therefore, this balance comes like this. Exactly like the case of planetary motion, where the gravitational force plays the role of the Lorentz force, and the Kepler law is derived like that. Okay, so you get a characteristic length psi, which we will remember because that length scale appears somewhere later. Okay, so now let's do quantum mechanics. So what you do in quantum mechanics is that instead of writing equations of motion, you first write what is the Hamiltonian. Well, this again we discussed in great detail in the first lecture itself, where we argued that from the Lagrangian, when you write the quantum Hamiltonian, you can introduce the Hamiltonian. It's 1 over 2m, and all that you do is, see, if you stop here, then this is your free particle quantum mechanical Hamiltonian, right? But you have to replace P minus PA over C, the vector potential squared. So this is something we discussed also in great detail about the various forms of the vector potential in the context of Baum effect as well. And what is the vector potential? The vector potential is defined such that curl of that vector potential gives you the B field. Okay, in this case the B field is of course just a constant field along the z-axis, so it is like this also. Okay, so now you expand and recall that we said that because of this relationship that the physical field is the curl of the vector field, you can add to that a gradient of an arbitrary scalar function. The curl will not change, so this is called gauge freedom, and so you can choose various gauges. Last time we used what is called the symmetric gauge. Today you'll see, because life gets a little simpler, we'll use what is called a Landau gauge. In the Landau gauge, the vector potential is defined as, this is similar to the laminar flow that we are discussing in the context of Baum effect. So this is the Landau gauge, where the x component is 0. The z component, of course, is always 0 because they have chosen the B field to be along the z-axis, and the y component is simply given by Bx. Okay? You can easily convince yourself by taking curl A that you will get the constant B field along the z-axis. So let's complete the square and put in this A field term, and so you'll find that your Hamiltonian now is 1 over 2m Px squared. Mind you, these are all quantum operators, so I indicate that by putting some hats there, plus 1 over 2m Py minus Eb over C x hat for P squared. That's what you get, right? Because you have Px minus Eax over C, but there's no Ax, so I simply get Px. Also for the z component, I have Pz minus Eaz over C, and I don't have any Az, so I simply get Pz. Only for the y component, there's some masala here, right? But just look at this. If you look at it, you see that your Hamiltonian does not have any y coordinate or z coordinate. Of course, it will not have any z coordinate if the moment you put the magnetic field be along the z-axis. That's trivial. The fact that it doesn't have any y component, y coordinate dependence also, is because of the choice of the Landau gauge. Okay. So what is the meaning of that? If one coordinate is missing, then what does it mean?
It's, I mean, its orbital
The corresponding
corresponding
momentum is a
momentum
good
quantum.
quantum